All right, hey, good morning. Today it's about vectors in a plane. This is Coach Stoney. Though listen. That was Beethoven's Fifth Symphony. And the reason I went ahead and did that, anybody recognize that? Da 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 da. Oh, I don't know what the heck happened there. So there we go. And now we're off. But that was Beethoven's Fifth Symphony. And that was three dashes. Dot 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 dash is the symbol V for the symbol. Is Morse code for the letter V, and we have vectors in a plane. Notice the V, da-da-da-da. So anyway, just a little side note there. Thought it might make it a little more interesting to start off with. So, but here we go. Oh, vectors on a plane, not snakes on a plane. I think we've used that joke before, but once again, we're talking about vectors on a plane. And we're going to start with magnitude and direction. Okay, let's find out what they are. Well, first off, this is what we know. Quantities such as force and velocity. Sounds a little like physics to me. And it is, a little physics today. Involve magnitude and direction. And you cannot be completely characterized by a single real number. So to represent such a quantity, we're going to use a directed line segment. A line segment like PQ, but we'll write it like this. There's only like half the arrow. For PQ, meaning you have an initial point at P and a terminal point at Q. And its magnitude or length is denoted by that, which is basically, think about it, length, going to be a little Pythagorean theorem there. Look at that distance. Take the 2 points, subtract them, and you will then have, in a sense, the distance formula. So like, in a sense, magnitude is kind of like the distance. So you can see the Pythagorean theorem formula there. All right? Well, the distance formula, which is part of the Pythagorean theorem. And here's our picture of it. The initial point P going to Q. And it's labeled like that. That means vector PQ, not ray PQ. If it had the other little line, it would be ray PQ, but this is vector PQ. Initial point and the terminal point. All right? And it's called the directed line segment as vector is a vector V in the plane, and it can be written like that. V can represent also that directed line segment PQ. All right? So what are equivalent directed line segments? Well, let's let U would be a vector represented by the line segment from 0, 0, which is our origin, to 3, 2. And let V be represented by the directed line segment from 1, 2 to 4, 4. And we're going to show that U equals V. And the way we do this, first off, I graphed them. Do they kind of look the same? Yes, but how can we verify it? Well, let's go to our distance formula and take our x's and minus them, and square it, plus our y's and minus them and square it to show the actual distance. So notice if I put in the 3 from x2 minus the 0 from x1 plus 2 from x2 minus that should be a 0 right there. And there we go. We get 9 plus 4, which is the square root of 13. Now that was PQ. So let's do the one for RS. And the RS is, notice the point 4 minus 1, and that 4 minus that 2 squared. Hey, it's also 9 plus 4. So here's the thing about it. They are equivalent because what? Their magnitudes or their lengths are the same. And also, what else has to be true is that their slopes have to be the same. So I can't quite say they're equal yet until I check the slopes. And notice the slope formula, y2 minus y1 over x2 minus x1. The change in y's over the change in x's. Rise over run. Remember, y is always on top. All right. Slope PQ, so I'm going to take that 2 minus that 0 over the 3 minus 0. My slope is 2/3. And I got to check the slope of RQ, which will be that 4 minus, no, that 4 minus that 2, and that 4 minus that 1 over the x's. And notice the slopes are the same and the magnitudes are the same, so therefore they are equal. So U does equal V. But in order to show they're equal, The magnitudes have to be the same and the slopes have to be the same. Otherwise, they're not equal. We could have the same length, but if we're not going the same direction, we're not quite exactly equal. All right? So now here we go. We'll talk about the